Okay, so we're in section 3 of the prerequisite stuff. So this is like hard of algebra 2. We're deep into it now. So we're going to be doing radicals and roots today. So we're going to do a bunch of vocab terms with this. Just make sure you know it. We're going to do simplest radical form for the most part. That'll be probably what we spend the most time on today, just because it's one of those things like unless you see somebody actually attempt it, that can be pretty tough. And then we'll do some properties once we get time. So what I mean by properties, basic operations, right? Add, subtract, multiply, divide, that type of thing. But then we're also going to look at, how you can rationalize, how you can use fractions in the powers to actually signify a square root. Those things can be definitely helpful, so we'll talk about that today. But yeah, so our goal is to kind of do a brief introduction today, kind of go through the basic stuff. Hopefully this seems a little bit better than what you probably learned in previous classes. Well, it'll make a little more sense to you, because this stuff is usually the part where I start to see people fall off. The first couple, assignments were kind of straightforward, but this one in particular is one that people sometimes don't like because they didn't get a good solid base before. It's right here at radicals, because it can be one of those things you either get it or don't, and sometimes people pass it and you don't. We'll try to get you filled in here. So, all right, well, homework's due today. Make sure you get that turned in. Appreciate it. That grade book, as of this moment, is up to date, other than the assignment due today. Obviously, everything is in the grade book, so you can kind of see what you're missing, what you have. I think all the grades are in. Okay, so ready to go? Perfect. Let's start. Let's talk about roots themselves. A root. Okay, what is a root? What is it? Have you seen before? What do you know about the word root? Most people have a wrong definition to it. I'm not trying to put you on the spot. But a root is when you're solving a type of quadratic or some type of polynomial equation, some type of expression, something like this. That type of problem. A root is the solution to that equation. I think some people have that misconception where it's a radical. It doesn't have to be. Like this one, the answer isn't a radical, but the root is the answer to it. So what we do to find roots for an equation like this, the trick was you take this power to the other side. So you always do an inverse operation. Well, the inverse of a square, that's a square, right? X squared, that's how we say it, X squared. The inverse, when we do the squared part, when we take it to the other side, is a root, it's a square root. So you're going to take the square root of 4. Now when you do that, there's two potential answers, there's a positive or a negative. That's just how it works. There's always a positive and a negative. People tend to forget that, because when you square something, there's two of them, the negative sign could have canceled out. When you do odd powers, it's 1. It's just there's one answer to it, positive or negative, and it depends on what your problem is. But anytime there's even powers, you're going to have a plus or minus. That's just how you need to think of it. Square root of 4, what this is, the answer for this problem, like when you simplify this, that's the root that I'm talking about. It's the answer for this equation, but it's simplified. Well, square roots, if you don't know, what you're trying to do is figure out what number multiplies on itself, exact number multiplies on itself, that gives you the number on the inside of the radical sign. Well, most people know 4 is 2 times 2, so the answer would be 2, but it's plus or minus 2. That's a root. It's the answer. There can be more than one answer to a problem. This answer has 2. Now the reason why there's 2, it actually, the exponent on the top, so the x squared, actually tells you potentially how many roots you have. We have 2 answers to this problem. That's usually what it is. Now if it's an odd power, that's the difference. If it's 3, there's not 3 potential answers. There isn't. There's 1 that I'm looking for, but it has potential to have as many as 3. But we'll start to learn that in the later sections, like how could there be 3 to a problem like that, and it depends on what the equation is working out. But that's what we're looking at. Now, the other thing to know is that, it's the answer for this, quadratic, this polynomial equation, but it's also the number of times it hits the x-axis. So on this particular problem, if we were to graph this, the answers are the potential, what we call the X-Intercepts. And that's the part that we're going to look at later on in this book. You know, I don't know if it's necessarily the next section, but it's coming up, where we start to graph really tough polynomial equations. I'm going to show you shortcuts for graphing. You look at, you know, inflection points, we look at min and maxes, we look at lots of different things. Hopefully stuff you've heard before in either Algebra 1 or Algebra 2, but we put it all together and I have like a simple, you know, checklist that we go through to make sure you know all the stuff you have to do to graph some random polynomial that I give you. There's little things we can do to it. Okay, but yeah, most people have the wrong definition. So, going through this, let's talk about the actual square root. Let's talk about this and let's talk about how to get these answers, right? So what you're seeing here, that is a radical sign. That's the vocab that's involved here. This is a radical sign. Now, most people know the type of root we're looking at here. You know, this is a square root. But on a radical sign, there's a number placed on the inside. Whatever this is, could be a number, could be variables, anything on the inside. Those are called a radicand. So radicand, whatever's on the inside, whatever you want to put in there. And then the number on the outside is the part that some people forget. The number on the outside is actually the most important number. It's the number in the little tail, the little like bend. That number is called an index number. Index number. It is the most important number you're actually supposed to look at first. Some people are never taught that. You need to look at the index number because that tells you how to do the radical in the first place. Now most times, if they leave it blank, like this problem, it's a 2. It's the one time in math you can assume it's a 2. Everything else in math is always ones, right? There's a, you know, a leading number out front of the variable is a 1. The power on it is a 1. But in this case, it's a 2. So, if there's any other number sitting there, they have to print it. Now, this is where you're going to see a difference. Your book does a pretty nice job of, you know, if it's a radical with a different root, they do a pretty good job of showing you the small number in the little index, you know, spot. But if I print it on a test, so I'm printing out a test or quiz, whatever we have, Microsoft Word for some reason likes to put it up here. Like it puts it way up. It's small, trust me, you'll see it. It's small, it's tiny, but they put it up. Just because it doesn't fit, or sometimes they don't want it to blend together depending on the printer. So they put it up. There's a clear difference between that 3 right there, because it is tiny, versus a big 3 out front. You can see a big difference on a test. So just be aware of that. Okay, questions on the radical sign, the radicand, the vocabulary that's involved. Okay, goal, again, going back to what we have over here, goal state, or to learn how to simplify radicals. To take anything, variables, numbers, anything, and actually break it down. That's what we're going to be doing today. So it's called simplest radical form. Now there's a difference between simplest radical form and principal square roots, and let's talk about that. On this problem, there was 2 potential answers, right? There was a plus or minus 2. Okay. Now, I know there's always 2 when we do radicals. Well, let's discuss. So let's go in, let's put a 16 here. Okay, so we're going to try to break this down, right? There's 2 ways to do it. Oh, you can go to that. Yeah, I figured it was coming. All right, now, you have your radical. We're going to break it down. So we're going to go to simplest form. So simplest form is when you're going to break this down into what the smallest numbers you can do that you can take radicals of it. So there's 2 methods of doing this. So one method is you actually memorize the perfect square chart. Perfect square chart will help you take square roots of numbers. I'll show you how to use that here in a little bit, but here's the perfect square chart. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 186, 225, and you keep going, and it just goes on forever. Now, it looks like a crazy random set of numbers. But how these numbers are created, you know, this is 1 times 1, 2 times 2, 3 times 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you get the idea, right? So if your number that's under the radical sign, if that number is on this list, it has a perfect answer. We'll know that. If it doesn't fit on that list, then you have to do what they call simplest radical form. You break down as far as you can until you can't do it anymore. There's the difference. Okay, if the number's in this list, it's the easiest problem in the world. Everyone knows, you're trying to think of a number, since the index number's a 2 here, they didn't print it, but there's a 2 sitting there. You're trying to think of two numbers that multiply to give you 16. That's how it works. So the two numbers will be 4 times 4. Okay, 4 times 4 is 16, so the answer is 4. Now it could be plus or minus 4. I always want the positive number. Since this is not an equation, you agree that this is not an equation and have, x squared equals 16 or whatever. It's just a radical. So I always want the positive answer. That is called the principal square root. Principal square root. Principal square root is just, I want the positive answer. That's what I want. It's different than simplest radical form. Principal is just saying that I want the positive answer. Now again, why it's 4? It's the fourth number down the list. So if you actually have all these numbers written out in order, and you just count, okay, 1, 2, 3, 4, that's the answer. Square root of 16 is 4. That's how you use the perfect square chart. Okay, that's breaking down by perfect squares. There's a completely different way to do radicals. One way that I think some people tend to overlook, but it's way simpler. Like you can do radicals like this without even having to spare a simple thought about it. All it does is it requires that you know how to simply multiply numbers, and you can make radicals really easy. Okay, but you got to know your index number. So we're going to go back to this as 16. So it has an index number 2, right? So here's how I do this. So if you got to know your index number, but to do this problem without doing perfect squares, without thinking about the chart itself, all I want you to do is break down 16 into numbers that multiply to give you 16, but not the whole list. Just give me any two numbers you want that multiply to give you 16, and don't give me 1 and 16. It's got to be any other number other than 1. Okay? Give me two numbers that multiply. 2 and 8. Okay. It could have been 4 and 4. You could have given me any number in the world. It didn't really matter. So you're the 2 and 8 person. Okay, you could have been 4 and 4 for all I care. Now, when you do that, keep breaking down the number until you can't go further. So obviously 2 is already broken up because I say you can't break it up into 1s. Let's break up 8. 8 is 4 times 2. 4 times 2, right? You keep going. You just keep breaking down the numbers until you can't break them down any further. Don't put any mental thought into it. Just break them down as far as you can. So the other number I can break down now is the 4. I can break that down even further. So, yeah. So this is going to be this. Right? So I broke them down as far as I can. So I broke down 4, broke down the 8 above that, and the 16. So this is where I'm at. I can't go any further. And my index number on the outside, what is my index number still? 2. It's important. You got to know the 2. Now that you know that, here's your shortcut for doing this problem with no mental thought into it whatsoever. 0 mental thought. If you look at the index number, it's a 2. What that's saying is I want you to circle pairs. 2 numbers that match. They can be in any order you want. I don't care if they're written in numerical order. If there's a pair, circle them. There's 2 numbers. So I'm looking for pairs of numbers. Well, there's a pair right here, right? 2 numbers that match, correct? There's another pair in the back. If there's other numbers that are pairs, circle those. It could be 3s, it could be 19s for all I care. Whatever pair, 2 numbers that match, you circle them. When you circle them, here's the rule. You cross one of them out, you kick one out of the house. Okay? And you do that for every pair that you've circled. You cross one of them out, you kick one of them out. So right now, what numbers are sitting on the outside of the house? There's a 2 and a 2 on the outside, correct? What's left on the inside of the house? Nothing. The bar goes away. There's nothing left. You had no numbers left on the inside. You kicked them all out. Well, what's 2 times 2? That's the answer. It takes 0 mental thought to do it that way. It's actually one of probably the fastest ways to do radicals safely. Safely, where you don't put any mental thought. You can do this for any type of radical. It works for all of them. 3rd, 4th roots, 5th roots. but it saves you from thinking about perfect squares. Okay, is there a 4 that goes in this, or is there a 9 or a 16? No, don't even care about it. Don't even think. You're putting way too much thought into it. You break it down into numbers that are simple, and then you use the index number to tell you what numbers to circle. Okay? To prove my point, let's do another one. Let's use this radical. Let's do the square root of, I don't know, 12. I'm just kind of picking a random number here. Oh wait, what am I doing? I put 72. Okay, 12. Okay. You agree that 12 is not a pretty number, right? It's not a perfect square like 16 was. So we do the exact same rule. You break down 12s. Okay, so 12, what are two numbers of multiplication? 3 and 4. Okay, a 3 and 4 type of person. Fine. Doesn't matter what type, 2 or 6, 3 and 4. Break down 4. Okay, so that's what, 2 and 2? In no particular order. And now the index number on the outside. Still a 2, right? I still have a 2 on the outside. So we're still looking for pairs. That's what the 2 on the outside. You're looking for two numbers that match. Well, we do have a pair. We do have a pair. So the rule is cross one out, kick one out. Cross, kick. If you can do that, you'll get your final answer every single time. So there's a 2 on the outside. Is there anything left in the radical? 3. You're done. That's your answer. Easiest thing in the world. Zero mental thought into it. Now, it works for other types of roots. So it works for cube roots. It works for fourth roots. Without having to think about the charts that are involved. So let's do a number like 36 or something like that. It's kind of a random number. Let's do a cube root of it. Let's see if there's an actual cube root. Well, 36 is not. So if you're thinking about the chart, if you're that person who wants to think about cube roots, it's a cube, right? It's got power 3. So cube roots are like 1, 8, 27, 64, 125, 216, 343. These are all the numbers that have perfect cube roots. 1 times 1 times 1, 2, 2, 2, 3, 3, 3, 4, 5, 6, 7. And it keeps going past that. But this number is not on the list. It's between 27 and 64. So it's not 3, it's not 4, it's some decimal between 3 and 4. If you're going to try to guesstimate the decimal. Okay, it's probably closer to 3 than it is 4. But doing it with my little trick, my little rule to get simplest form. Two numbers that multiply give me 36.
6 and 6.
Say it again? 3 and 12? Okay. 3 and 12. What was the other list? What was the other number I heard?
6 and 6.
6 and 6. Okay, you do either way, so maybe that's 66%. Okay, now when you do this, make sure you leave the little index number out there. You have to print the index number. It is a cube root. Don't lose it, because if you lose the index number as you're going through your problem, whatever way you're doing it, if you lose it, then I count it wrong on homework. Especially if it was supposed to be a cube root and you got the little 3, it is wrong, because you just changed the type of radical. Okay, but either way you did it, that's fine. We break it down. 12 can be broken down even further if you're that 3 and 4 person again. Or if you're the 2 and 6 person, don't really care. Break down 4 even further. 2 and 2. All right. So now, index number on the outside is a 3, correct? So what we're looking for is 3 numbers. We're looking for 3 numbers that match. Do we have 3 numbers on the inside that match? Like a triple of numbers. We don't, right? That means you can't break this down. It's simplified already. Since there's not a triple of numbers, whatever they are, 4s or whatever they are, even though we break down 4s even further, but whatever they are, if there's not a triple of numbers, you can't break it down. The final answer for this problem, the simplest form, is just that. That's it, the simplest form. You can't do anything. Since you broke it down all the way, there's no triples, there's nothing you're kicking out of the house, the answer is just the cube root of 36. You just multiply them all back together. Now, if there was a triple, let's say we had the number like 24. This does have a triple in it. So you break down 24, same rule I just showed you a little bit ago. Let's go with like 3 times 8. Then you're going to break down the 8 to be 2 times 4. You break down the 4 to be 2 times 2. To be that. Right? So you broke down as far as you can. We do have a triple of numbers. You have a triple. You have a triple set. Because again, why I'm looking for triples, the index number tells me I'm looking for 3 numbers that match. I have it. Boom, they're right there. So the trick is, if you have a triple, and you could have multiple triples in there, I don't care what numbers they are, it could be 2s, 5s, 7s, I don't care. The trick is the same. You cross them out, and you kick 1 out. It's the same rule I just did a little bit ago. You cross them out, you kick only 1 of them out. That's how it always works. So they should be gone. So the 2's on the outside. The 3 was left on the inside. That's your answer. That's simplest form. It works for 4s, it works for 5s. In fact, the reason why I like this, the reason why I show people this, is because you can do this with variables as well, letters. So you can break them down into, to actual sets, so you can get to what they call simplest radical form for variables as well. Now there's a clear difference here, and I'll kind of show you what I'm talking about, but does this make sense, like the concept of what I'm doing? Cross them out, you kick 1 out. If there's 4s, so if I'm looking for, quartic root, right, 4th root, then you're looking for 4 numbers that match, and you cross them all out and kick 1 out. That's how it works. Okay, let's do one with variables. Same thing. So let's go with number 75, x squared y to the 5th z. So we're doing a square root. We're going to try to break these down. I can show you different ways to do this later, but this is, again, trying to stick with my same pattern so you don't have to put any mental thought. Even though this one has variables and it has, letters, you can still do the same rule. So what are numbers that multiply using 75? 25 and 3. And then for the variables, you just do the same thing. You just break down those variables. X and X, you have a bunch of Y's here. I know this seems tedious, but and a Z. This is all on the ground. Then you can break down to 25 even further to be 5 times 5. I'm just going to go to the chambers here. Going right to it. Makes sense in the breakdowns. No thoughts into it whatsoever. Now that you have that, now what we're looking for is the index number. Index number is a 2 on this problem because it's not printed. The square root, so it has a 2. I'm looking for pairs. It can be anything. Well, I do have a bunch of pairs in here. I have a pair of 5s. I have a pair of X's. I have a pair of Y's. I have another pair of Y's, and that's about it. So you circle whatever pairs you have. And again, circle them so you don't forget. What's the rule for the pairs now?
Cross one out, kick one out.
Cross one, kick one. So cross, kick, and you get the idea. Cross and kick. So on the outside, there should be a 5, there's an X, there's a Y, there's another Y. And these are just being multiplied together. Those are all going to the outside. On the inside, what's left over? 3Y and a Z. Boom. Boom. And now I can combine and I can get to my final answer. 5x y squared, there's 2 y's on the outside now. And on the inside I have the 3y and a z. Now, the only difference, so you look at the back and boom, there it is. The only difference the book will have, and this is something I want to talk about, bless you. The only difference the book will have is that the variable for x, the variable x on the outside, they're going to put an absolute value bar around it. I know that seemed a little goofy, because that's the way you're supposed to do it, but they're going to have this in the back. Can somebody explain why they would have that in the back and not that? Why would they do that? Why would they just suddenly throw in an absolute value bar?
X squared has an even power.
Okay, x squared had an even power, you are correct, and it went to odd. It went from an x squared in the beginning of the problem, it went to x to the first on the outside. And the other thing is, it's getting down to what I said earlier about when you're doing roots, I want the principal square root. I want the positive answer, right? So you're technically there. The way to guarantee that that answer is positive is to make sure that the x turns out to be positive, because that's what absolute values do. They guarantee it's positive. The y squared, why they don't have one around the y squared, when you square something, it's always positive anyway. So the power on the outside became, this was an even, it was squared. They didn't need to put an absolute value first because it was already guaranteed to be positive. They had to guarantee this one was because the power was odd. So that's the trick. Do I require it? No. If you get down to that answer in green, I'll give it to you. You're getting the most part down, you know what you're doing, but I want you to be aware that if you go to a college level calc course or whatever, pre-calc or whatever level you're at in college, they'll probably require you to use absolute value bars because they want to guarantee that you're getting the positive answer out of that thing. And I want you to be aware of where that comes from. So, well, like what Abby said here, it went from squared and it went to an odd power on the outside. It went to x. You got to guarantee you got to make it positive. You got to put absolute value bars around. Now, you only have to do this if that's an even type of root. Square root, fourth root, sixth root, whatever it is, you just have to make sure that it's an even power that the bars are. Okay, questions, comments, everything about it. Okay, I know that was kind of the quick crash course into something you probably learned over a couple of days in Algebra 2 maybe, or even more. I don't know how many days you spent on that.
Probably not.
Okay, well, fair enough. All right, so I just want to make sure that you see the easiest way to do those problems, so you're not getting hung up on that. All right, that was simplest radical form. You're breaking down things as far as you can, and you're guaranteed that I get the principal square root out of it. Again, it works for any type of radical. Now, we're going to come back to this probably tomorrow more when we do those, the powers, when we start changing powers, and I'll show you a shortcut for doing variables tomorrow with that. It may not even be a shortcut to you, but it is to me. But let's go to the properties. Let's go to the basic stuff about radicals. Just start and stop the camera here so we can keep going. Okay. Okay, so let's do a basic property. Let's talk about multiplying radicals. 18 times 15. And these can have variables in them, they can have anything. You can multiply any type of radical together. It doesn't matter what the difference is. I mean, the 15 back here can have an x in it. You can multiply them together. Make sense? You can multiply them. As long as they're the same type of root, you're allowed to do that. I can show you shortcuts for doing other types of roots later, but okay, now that we have this, we're going to multiply them together. There's different ways you can do this problem. I think, because some people like to break it down and simplify first. There's a reason why that can be helpful. I usually just, when I put them together, I don't actually multiply. I do something like this. I just put them next to each other. I don't take 18 times 15. Silly, don't do it. Now that I'm here, we're going to do the same steps we did over there to simplify the answer down. This is called a product rule. You can go from two separate radicals to one single radical using this rule. Then you just break it down from there. You're allowed to do it. And vice versa. If you have one radical, you can separate it into two separate ones. In fact, that's what I'm actually doing over there. I'm actually taking individual square roots of all of those terms separately. That's what I'm doing. So now that we have this, 18 is, what is that? Let's go to 9 times 2. 15, 3 times 5. And times x. You can break down the 9 even further. Now that we're here, what type of radical do I have? Index number 2. Index number 2, they don't have it printed, so it is a 2, so I'm looking for pairs. Well, I only have one pair. That's fine. You have one pair, kick it out. So cross one out, kick one out. So it looks like my final answer, simplified version of this, is a 3 on the outside, 2 times 3 times 5, that's what, 30 on the inside with an x. This is the simplified version of this problem. Now the actual answer, like if you were to multiply 18 times 15, I think that's like 270 or something like that, x. You didn't have to go to that. I just want you to be aware of like that you can just go from here and just start breaking it down right away. Questions at all about the original problem and how to simplify something that's being multiplied together? Okay, any type of variable, they all work. Now, if there's numbers on the outside already, this is one that the book throws at you sometimes. They do something like this. And let's put a 7. Okay, let's say that they're not the index number, they're just the leading numbers out front of the radicals. These will just be multiplied together on the outside. Those carry down. So then you'll have the 2 times 7 times 3 on the outside. So eventually I have the 42 out there. 2 times 7 times 3 is 42. Questions if they have leading numbers, leading coefficients. Because I think of a radical like a variable, just like an x. You can multiply the numbers out front. Okay, that's the product rule. Quotient rule, this will probably be my last property today. This will be my last one. We'll do addition, subtraction, tomorrow and stuff. Last property here, last example. We're going to do division, right? Quotient rule. 15 x squared, and we're going to divide by, let's go 12. This is all in a radical. What the question usually is it says rationalize the following fraction. That means rationalizing means you're not allowed to have radicals on the bottom. It's not a rational number. Okay, I know that, for the most part this will be irrational, it has variables in it, but the one rule in math is you're not allowed to leave radicals on the bottom of a fraction. You're not. So you're going to make the bottom number a whole number. Now, to make these problems easier, you could break these down and you could go into 2 separate radicals like this. This is called the quotient rule. You're allowed to do this. Separate them out. And you could go from there and do your thing. You could still do that. You don't necessarily have to. Some people do. They like to do that. They break everything down. They see what they can do with it. I'll go both directions just to show you the answers turn out to be the same. What I would do personally, if I was in a problem like this, I would simplify the fraction first before I start breaking them up and then carrying numbers around. Because it might make the numbers easier. Like for instance, 15 and 12 have 3 in common. Divide them both by 3. Now that you do that, now you can start to see that the number on the bottom, you can actually take a perfect radical. Excuse me. You can actually take a perfect square of that square root of 4, or of the 4. So you can still do the quotient rule, like such, but now that number is just a perfect number. So the square root of 4, that's just 2. And then on the top, I can't break down 5, but I can break down the x's, and I can kick one of the x's out, because there's a pair. So it looks like my final answer would be an x on the outside, and you probably have to put a radical around it. And a 2 on the outside. Or not a radical, but an absolute value, or this was the back of the book, probably have to guarantee it's positive. Okay, that's the answer, right? That's easy. You break down. That's rationalized. The bottom number is a whole number. It's not a radical anymore. Now on the top, how you do that type of problem is most people would break these down. So 15 is 3 times 5. And you have an x and x. The 12 on the bottom is 3 times 4, which is 3 times 2 times 2. The 2's can get kicked out, and then the trick is to simplify the 3's as well. But on this one, why this would take more steps, is you kick the 2 out on the bottom. The top, you kicked out an x. There's still a radical 3 on the bottom. So it's the same problem, just doing it two separate different ways, right? So you can see this. On the top one, over there in green, there's still the 3 on the bottom. So the trick that they always tell you is to multiply by whatever that number is. So if it's a square root. If it's any other type of root, they show you a shortcut for doing those. But since it's a square root, you're going to multiply the top and bottom by the square root of 3. That's something we need to talk about tomorrow. Like the reason why they would do that, and what it would be if it was a different type of root. But that's the rule for how you simplify if there's numbers in the bottom you can't get rid of, like the 3. Because on the bottom, you'll have square root of 9, which actually simplifies. And on the top, you'll be able to simplify that as well. Okay, questions with rationalizing. We're going to talk about that tomorrow, that whole concept of why they multiply by the radical 3. Okay, we're good with what the quotient rule is, concept behind it? All right, we got a couple minutes left here. Homework's due today if you haven't turned it in already. Okay, I think we got JV football tonight. Is that all right? We have cross country for sure and volleyball. So is there football tonight?
No,
JV?
I don't think so.
Okay, I didn't know. I didn't know if they just carried over from yesterday. Okay, so I think everything is in what, Belmont tonight?
Yes.
So there you go.